This video illustrates an application of the Dynamic Maximum Coverage problem, DMCP. The DMCP generates trajectories that maximize the coverage of areas that evolve over time and due to systems actions. The DMCP can be applied to numerous other cases, such as scattered intervention, security task, preventing illegal activity, and planning for rescue operations. Gathering problems, such as collecting observations. In this video, the DMCP is applied for performing multi-robot bodyguard operations. We want to optimize the trajectories of a team of robots for best covering the surroundings of a moving VIP. As challenges, the VIP moves at irregular speeds, sometimes faster than the robot, and some obstacles block the way. The robots need to anticipate the future moves of the VIP, tightly coordinate and integrate advanced goals. The robots have heterogeneous capabilities. They have different speeds, vision radius, capabilities for low light vision, and capability for pushing obstacles. In this scenario, the system aims to cover the evacuation of a VIP. The VIP should move from here to there. We want the back of the VIP to be covered here and there too. Note that this area is in low light and thus requires low light vision capabilities for best coverage. Moreover, we want the system to anticipate the future positions of the VIP. When the VIP hides behind that wall, we want the hole to be covered. Then, we want a robot to secure the exit corridor before the VIP reaches it. Last, some obstacle block the way and line of sight. Robots must remove this obstacle in order to move forward. In addition, they get a penalty if the crates are not removed by the time the VIP needs to cross that part of the corridor. The system consists of 3 robots, 2 Nerva robots and 1 Semitic cell robot. DMCP, through its advanced world dynamics, coverage and reward function, enable for defining such a situation. The system has been implemented on real-world robots. Here are the trajectories generated by our algorithm called best response. As a general trajectory, the robot team splits in 2. Nerva 1 will cover the south corridor while the other 2 move to the north. Then the Semitic cell will rush cleaning the crates while the Nerva 2 slightly anticipate the moves of the VIP. Once the crates are cleaned, the robots reorganize themselves. The Nerva 2 continues anticipating the trajectory of the VIP up to the exit corridor. The Nerva 1 protects the rear of the VIP and, when reaching the hole, moves to the corridor requiring low light vision. The Nerva 1 then switches with the Semitic cell, which then covers the rear. Here is the same scenario coupled with real-world footage of the operating system. The robots split in team. The Nerva 1 reaches the south corridor while the other 2 go north. Here you can see an example of tight coordination. The Semitic cell stops for best covering the corridor. Then, when the Nerva 2 arrives, the Semitic cell starts moving ahead for compensating what the Nerva cannot see. Soon after, the Semitic cell rushes through the corridor and cleans the crate, so the Nerva can cross through. Next, the Semitic cell places itself in the hole and starts watching, waiting for the Nerva 2 to come. As an example of tight coordination, the Semitic cell replaces itself when the Nerva 2 comes by. This video demonstrated the feature of the dynamic maximum coverage problem. Notably, it showed that the DMCP is very relevant for handling advanced coverage problems with detailed world dynamics, coverage and reward models. Moreover, this video highlights that these problems enables for the generation of trajectories that offer tight coordination and anticipation for complex scenarios. Thank you for watching this video.